Hi, my name is Ramdas Kachari. I work at Memory Solutions Lab, Samsung. I lead a group, data center device solutions, that is focused on developing new features and technologies relevant for data center storage infrastructure. Um, Processing data in storage device is not a new concept. It's been there for quite some time. However, recently it has regained attention and focus with the advances in digitalization of our society. As more and more aspects of our lives embrace digital technologies, a lot more data is being generated and processed. And computational storage technology has a potential to play an important role, a critical role in that in that new technology. So we'll look at what it would take for this computational storage technology to become successful and become widely adopted for this new data center infrastructure. So let's look at why computational storage technology makes sense for this new modern data center infrastructure. So various applications such as social networks, autonomous driving, virtual reality, online games, etc., are generating humongous amount of data, and that data generation and storage rate is growing continuously, somewhere close to 20% CAGR. So all this data that's being captured and gathered must be monetized, and for monetization of that data must be processed. So some example of using data to improve productivity and of applications and user experience are recommendation systems that recommend users various choices and options regarding shopping or entertainment content. Yet another example is Tesla insurance. For example, Tesla is collecting all this data regarding the driving habits, and that data is used to provide optimal, more suitable and optimal premiums for safe drivers, basically. So data is being used to improve productivity of applications and make user experience smoother. So with that, the efficiency of data processing becomes important because compute resources do have cost, and there are trade-offs with respect to cost and performance. So CPU cycles, memory bandwidths, memory footprints, network bandwidths, etc., play a role in that data processing cost. And energy is one another aspect of data processing, and with current statistics, it is becoming a major portion of overall power consumption by data centers. It is reaching levels where data center power energy usage at times exceeding entire electricity consumption in certain nations, basically. So it is a huge portion that needs to be optimized, and computational storage can help reduce some of those costs. So let's look at some of the basic principles of computational storage. On the right top side, it's a simplified system architecture diagram. So there's a CPU and system memory that's connected to CPU. A computational storage device has media, flash media, as well as computational storage memory and accelerator and compute engines that operate on that computational storage memory. So for computational storage use cases and applications, there are three phases primarily that are utilized. The first step is to load data into computational storage memory for processing, and data may originate in a host memory, or it may originate in flash memory. So then the accelerators and the compute engines are triggered, and they process the data sets that are kept in computational storage memory, and the results are then moved either into system memory or back to persistent storage. So computational storage enables a reduction in unnecessary data transfers. by processing data in storage device. So on the bottom right side, these are some of the scenarios where computational storage can help. So in the first row, data set is present in host memory, and that is transformed, process, and that process result is moved to a persistent storage. Now this can be offloaded to a computational storage device as a inline data processing use case. In the second row, it shows data set originates in storage and it's moved to host memory, and a query-like function is run on that data set to obtain results, and that results in a reduced data set, and that could be done in computational storage device, and thereby avoid copy to host memory. Yet another scenario where data present in storage memory is processed, transformed, and then again returned back into the flash or storage media, and that could be a offload opportunity to do this offline kind of processing. So by processing data as soon as possible, it reduces latency as seen by applications. It eliminates some data transfer and data hops involved in movement of data. So that's the basic premise and principles of computational storage. Here are some examples where example applications where computational storage can help. So for example, search in storage, huge data sets can be searched in a fast and efficient manner. Scan heavy database queries can be accelerated by performing those queries in the device itself, and moving only the results into the host memory. Similarly, video processing and storage services such as compression, encryption, and media management such as media scrub or integrity checks, etc., can be offloaded to a storage device. So with that, so Samsung has been at the forefront of computational storage technology development for last several years, and working with our partners, we have productized smart SSD. So based on that experience, here are some observations and learnings. So there is definite value in computational storage. It enables and allows efficient utilization of flash bandwidth by processing data as soon as possible and at the maximum throughput that flash channels can allow. It helps reduce TCOs and system resource costs, as well as it enables lowering latency experience by applications. However, there are many applications that can benefit from computational storage technology, and that brings to this observation that different use cases have different requirements. So that's a big range, and value proportion for different use cases and customers may differ. Some use cases customers may be interested in TCO, yet some other customers users may be interested in performance or latency or throughput, etc. So having a single device or single architecture may not provide optimal solutions to every possible use case. Cost and power are extremely important, and for end users to be able to use computational storage technology, if it incurs additional costs in terms of different software pieces or hardware or other aspects, that would minimize the net value that's provided. So having optimized architectures that are fine-tuned and targeted towards specific use cases or set of use cases may make sense, and that could be one way to realize full potential of computational storage and bring that value to customers and end users. So with that, to be able to create those optimized architectures, one aspect to solve that challenge is to understand use cases, the requirements, and the requirements of infrastructure on which those applications run. So here I have tried to categorize these different requirements into these 4 buckets. By no means this is a complete list. Also, some of these requirements may be more important for certain use cases and may not be that important for others. So that's all possible. So so the first bucket is development related requirements, what it would take to develop a CS application, how easy or what skills are required to develop acceleration engines or offload functions. Runtime, once you have your computational storage application running, does it meet performance functional expectations? What are the platform or data center infrastructure requirements from computational storage solutions? And then finally, to deploy this technology, what would be the requirements that these solutions must address? So so many of these bullets and the requirements can be big topics in their own rights. However, so here I am trying to outline and enumerate various requirements that need to be considered. So ease of development is very important for enablement of computational storage technology. If it's too difficult to develop, or if it needs very specialized skill sets and resources, that would minimize wide adoption. IP reuse. Customers and end users do have the existing solutions that may be running on x86 or maybe using accelerator cards, etc. And if they can reuse as much as possible, that would definitely help adoption of this technology. Portability is yet another important aspect, that once you have computational storage application and solution, it will be very desirable for users to be able to move to different vendors and providers and not get stuck with a specific offering. So here are some more development time requirements. Compute resource type. Different applications may benefit from different kinds of compute elements in a computational storage device, and so that may provide a better, more optimized value and solution to specific applications. So that needs to be considered. Easy systems stack integration is extremely important. If it's too difficult to integrate or coexist with existing software stack, that would minimize adoption. Ecosystem standards-based interface to the device would enable and help adoption of this new technology. And finally, quick GTM is extremely important. Once developers develop certain solutions, they should be able to change or modify or upgrade those features easily, and that would enable development of applications faster. Okay, so with that, let's look at runtime requirements. So even though computational storage device performs data processing on the device side, the intelligence still stays with the host, and orchestration of this processing is still controlled by host. And that orchestration efficiency becomes very important. If the interface between host and device is too chatty, or it has performance impact, that would not be very desirable, and it can reduce net value of the solution. So the device operation must be predictable, so that the applications know what to expect when they offload some processing to storage device. Error and exception handling is another important area where errors and exceptions will happen. However, those must be handled gracefully. And then the fallout of those error condition should be deterministic and not have undesirable side effects. It would be helpful to for devices to capture sufficient diagnostic data that can be provided to host layers, so that a quick debug of those error conditions can be performed. So moving on, let's look at some of the requirements for the infrastructure that um, on which those user applications might be running. Of course, the wide range of servers are present in data centers, and the computational storage device must work on those different servers. Right form factors is important. Um, Different users may have different needs in terms of form factors, powers, and server compatibility. Power and thermal budgets may differ from user to user or application to application, and a computational storage device will need to be able to throttle performance as needed based on the power and thermal budgets that are given or that are available. That performance throttling needs to be smooth, otherwise it will impact user experience. There are some more platform requirements that will be important to address. Scalability. Multiple computational storage devices will need to coexist in a chassis from capacity point of view or reliability point of view to be able to operate in RAID or similar environments is important. And then finally, these devices must support various operating system environments that may be present, including virtualized environments and hypervisor based systems. Then finally, we get into deployment related requirements. Once you develop the solution and it meets other functional and performance requirements, it becomes important that how do you manage this new resource that is offered by a device to the host. So discovery, configuration, initialization, monitoring, etc. Aspects become very important. The solution must be transport agnostic, as applications may move from direct attach to remote direct attach system architectures. It would be very desirable to have same application running in these various system architectures. So on the right hand side, the diagram shows a simplified version of direct attach and remote direct attach storage system architectures. Diagnostics and upgradability aspects. When the errors happen or when the exceptions happen, the in-field debug and diagnostics becomes very important aspect, as well as upgrade of firmware shells, platform shells, or kernel acceleration engines, etc. Becomes a important aspect for operational purposes. Privacy and security of uploaded functions is another big topic that must be addressed. Uploaded functions would like to remain transparent to actual CS device, or not reveal some of the processing that they do to the devices, and that must be supported. When certain functions are offloaded into computational storage device, it is important to have enforcement or protections so that those functions do not interfere with normal device operation. And then finally, the question about roadmap, that once you have something deployed, how do you use that for new applications or make changes or add new features to existing applications, and that process needs to be smooth. Okay, so with that, there are so many different requirements, and that can be summarized into this one possible recipe for wide market adoption of computational storage technology. Essentially, I think it boils down to making application developers' life easy. If it's easy to develop, debug, and deploy, that would make computational storage technology far more appealing. Similar to software-like development flow, where developers go through these cycles rapidly and easily. Flexibility of solution is extremely important. That oftentimes users and developers need to make changes to the solutions, and if that change process is is smooth and easy, that would definitely help. Finally, standards plus SSD operation. Even though it's this computational storage device offers this new compute resource and additional features, the storage functionality has to operate at full performance and as a normal SSD, and then computational storage features operate on top of the base storage functionality. So with that, there are many pieces to this this challenge to realize full potential and value of computational storage and bring that value to customers. Many pieces need to fall in place, and that would need a close collaboration between end users, vendors, academia, to find value propositions and validating those value propositions. It is extremely important for us as industry to find which applications and use cases may benefit from computational storage, and what are those needs. It is also important to develop new system architectures to take benefit of this new technology and a new compute resource that a computational storage device offers. And then finally, ecosystem development is a must for wider adoption of this technology in terms of standardization, reference designs, examples, and tools and open source. So we as an industry has a lot of areas to collaborate and realize full value and benefits of computational storage. So with that, that brings me to end of this presentation. I hope you find this presentation useful. You find something interesting, important takeaway from this. If you do have any feedback or comments, please share with us. Thank you for your time.